Alright, so this should be around October 26th, and we're going to do integration by parts. So a lot of things can't be integrated, but some things can be adjusted so that we can integrate them, like we use U substitution, and so U substitution allows us to integrate some things. So product of functions. So if we had, if we're going to take the derivative of a product, so a function u and a function v, then we would use the product rule. So we would take the derivative of the first thing, which would be du, times the second thing, plus the first thing times the derivative of the second thing. Okay. Now, to shorten this up, I'm going to let du dx, I'm going to use du for that, and dv dx, I'm going to use dv for that, just to shorten that up a little bit. So, if we integrate this, and we integrate this, we integrate this, then what would we get there? So here we would have uv, and then here we would just have those two things, except I'm going to rearrange them a little bit. So we would have v du, and then we would have u dv. Okay, so if we solve for this and we subtract this from both sides, then we would end up with the integral of u dv equals u times v minus the integral of v du. So one way to remember that, I just heard it this summer, was ultraviolet voodoo. Ultraviolet voodoo. How do you spell voodoo? I guess I could have looked that up. So ultraviolet and then voodoo, VDU. So if you need help memorizing that. So what we've done is expressed the integral in a different way. And then when we've done that, what we want to do is be able to, so you want dv to be a function that can be integrated, and you want u to be a function whose derivative is typically simpler than u. So one way you can do that is with this little acronym, Li8. So that tells you kind of the order in which you're going to try to substitute stuff out. So start with logs, and then inverse trig functions, then algebraic, then trig, then exponential. So that's how you would want to substitute. So you can read this stuff. Let's see how we do it with an example here. So we see this here. So we want, when it says let u be a function whose derivative is typically simpler than u. So when you take the derivative of u, it gets easier, is what we want to do. So I'm going to put u right here, and then, so we're going to start off with u here, and then we're going to put dv over here. So u, and we want dv to be something that's easily integrated. So the derivative of natural log of x is 1 over x. So 1 over x is probably simpler than the natural log. So if we let u be the natural log, so this is going to be u, and this is going to be du. So we're going to go down, we're going to take the derivative. Alright? So the derivative of u, the derivative of natural log, is 1 over x. Okay? That would leave us with dv to be x cubed. So that's dv, and in the formula we need v's, u's, du's, and dv's, so we need v. So to get v, we're going to go this way, and we on this side, on v, we're going to integrate. Okay, so if we integrate that, we add 1 to the exponent and then divide by the new exponent. So that's going to be 1/4. Now, we want to put that back together into this formula. Okay, so that's the beginning part. Then we need u times v. So u times v is going to be right here. So that's going to give us u times v. So we want to put 1/4 x to the 4th times the natural log of x. I don't really want to put stuff after that because it might be confusing if it's part of the log or not, the natural log. So that's the u times v, and then the next part here is going to be the integral minus the integral of v du. So v du is this way, these two. So, because this is v right here, and this is du. So that would be 1/4 x to the 4th, that's the v, and then the du is right there. And that would be, I could have put, when I, dx right there. Okay, remember we take the derivative of x, we put dx dx. Alright, so if we simplify that, let's see what we have here. So that's right there. This we can actually integrate. So if we integrate that, that would be, let's simplify this first. So I'm going to take out that 1/4, factor out that 1/4, and then this is going to be x cubed. Okay, so now when we integrate this, we add 1 to the exponent, divide by the new exponent, so that's going to give us x to the 4th and another 1/4. And so that's where we're going to get this. All right, we already had that. And then we integrate this. I don't know if you need to see that or not. Okay. Now, we can take the derivative to check our work. Now, probably not going to have time to do that all the time, but we can do that right here. So if we take, we're going to have to use the product rule here. So we take the derivative of the first thing, the 4 will come down, that'll be x cubed. So that's going to be x cubed times the second thing, natural log of x, plus the first thing, which is 1/4 x to the 4th, times the derivative of the second thing, which is 1 over x. And then minus the derivative of this. So if we take the derivative of this, we bring the 4 down, that's going to be negative 1/4. And then subtract 1 from that, that's going to be x cubed. So if you look at this, that's 1/4 x cubed, and that's negative 1/4 x cubed. So those are going to cancel out, and that gives us what we had originally there. So that kind of shows that that works. Okay, so we just want to memorize the process, and then see what we can do in different situations. Alright, so let's try it again. Maybe you could pause the video and see if there's some stuff you could do here. So your basic idea is you're going to have u. I guess I could put u here, u and du. guess you could leave those there. All right. So you've got that. Over here, you've got dv and you have v. So if you just kind of keep that in mind as your basic thing there. Okay. So how would you decide which is going to be which here? So if we said we want the derivative of u to be simpler than u, so if we chose e to the 2x to be u, and we take the derivative of that, the derivative of e to the u is e to the u times du. So that would be e to the 2x times 2. So that would be 2e to the 2x. Well, that's not really any simpler. We didn't make it simpler. So we probably don't want u to be e to the 2x. But what if we let u be x? Well, the derivative of x is just 1. So that's simpler. So that was okay. So on the other side over here, we want to, so that would leave us with e to the 2x here. Now if we integrate that, we would kind of need a u substitution unless we can do it in our heads. So we know hopefully it's got to be something similar to that. Now if you take the derivative of this and we want to end up with that, think about what you have to do. Now we could just do a u substitution over here on the side if you need to. So if we're integrating, remember here we take the derivative, here we integrate. So if we're integrating to go down here, we want to integrate e to the 2x dx. So you would let u be 2x and du would be 2dx. We don't have an extra 2, so dx is equal to half of du. So we could do that, half, and then we would have eu du. And the derivative of that is just, or the integral of that is just e to the u. And then we would substitute back in, so we would get that. Now, hopefully we don't have to do all that. Sometimes we can just kind of look at it and figure it out. So I know that if I take the derivative of this, I'm going to have to multiply by 2, and there's no 2 right there, so I need a 1/2 right there. So maybe you could do it that way. Let's see what's going on. So ultraviolet voodoo. So ultraviolet is UV. So we're going to have UV like that. So that's going to be 1/2 x e to the 2x. Okay. Minus, and then we're going to go this way. So that's kind of nice because there's nothing there. So that's going to be 1/2 the integral of e to the 2x. We have the dx from there. Okay, so this part we have here, and now we want to integrate that, and it's kind of going to follow that same pattern. So we're going to have that negative 1/2, and then when we integrate this, if we use the EDU method, we would get 1/2 e to the 2x, and that's going to give us the 1/4. And then we have the plus c. Okay? It gets much worse, don't worry. Alright? So, maybe you can pause and try this next one. Alright. Now, this may seem odd to you. You might say, like, well, what's the deal here? So remember, we're going to u and du on that side. So just remember this basic pattern here, and then dv and v. So we want u to be something that we can make simpler when we take the derivative of it. And if we use that light mnemonic device, a memory device, like Roy G. Biv, light, logs. So usually logs are the first thing we want to try to get rid of, because we take the derivative of the log, we're going to get 1 over x. So that's simpler. Now the trick here is, what do we want? Well, there's not much left. We could put dx over here. So if we integrate dx, we just get x. So if we go back to ultraviolet voodoo, so ultraviolet UV, so that's going to be, except I'm going to put that in front. So we're going to get that. And then minus the integral of this. Well, if we do that, that's just dx. Put a 1 dx if you want, but you don't have to. Okay. So if you integrate that, you're going to get, well, that is just right there. And then if you integrate 1, you just get x. So there you go. Now if we wanted to check that, we could take the derivative of that and make sure that we end up with a natural log. Okay. All right. So now, let's see what happens in this next one. So, we've got a u and a du. Yeet. And then we have, I don't know what that sound is about. All right. And then dv and v. So, this one's a little bit trickier as far as what you're going to pick. So remember though, one of the rules, if you go, I don't know if I read them all out or not, but one of the rules is when you pick dv, you want it to be something that integrates. So if you look over here, is there something that integrates in here? So hopefully, I don't know if any of you, it'd be nice to actually hear you try to answer, but hopefully, maybe somebody secant squared x, right? Secant squared x is a derivative. Secant squared x is the derivative of what? It's the derivative of tangent. So, one of our things that we try to do is pick something that we can integrate. So, that means that secant would be u. Secant times secant squared is secant cubed. Alright, so the derivative of secant, hopefully you remember your trig derivatives. We reviewed all this stuff from the notebook. So secant tangent. So the derivative of secant is secant tangent. Alright, so now how do we pick that? That's a derivative. We can integrate something we can integrate. That's how we, so our whole thing started right there. All right, ultraviolet is right here. So that's going to be secant x tangent x minus ultraviolet voodoo. So v du, that's this way. So that's going to be secant x tangent squared x. I didn't put the dx on there. Dx. Okay. So, when we look at this, let's look at this right here. So we want to integrate that. It might be easier if we just had one trig function. So tangent squared, that should make you think of the Pythagorean identities. So you're going to go sine squared plus cosine squared equals 1. And we want to get tangent. Tangent is sine over cosine. So I'm going to divide that by cosine squared. So that's going to be tangent squared plus 1 equals, and 1 over cosine is secant, so that's going to be secant squared. Remember that because it's the opposite. Cosine goes with secant and cosecant goes with sine. Okay, so tangent is equal to secant squared minus 1. So we can, so we have secant, tangent, and then minus, and we're going to have secant times secant squared minus 1. Alright, so one more there. We're going to put secant, tangent, and then we're going to separate this. So this is going to be secant cubed, and then that's going to be minus, that's going to be plus the integral of secant x. Okay? Now, if we go back to our original problem here, we had the integral of secant, oops, that looks horrible. Secant cubed x dx. So if you look at that right there, if we add integral of secant cubed x to both sides, we would have 2 secant cubed x dx equals, and then we would have secant tangent, and then we would have this little integral down here, and that is the natural log of secant plus tangent. Now, I'd be surprised if you have that memorized. That would be pretty impressive. So that might be listed on in your book somewhere. The integral of secant. So hopefully the integral of cosecant would be negative natural log of cosecant plus cotangent. It might be minus. I don't know, it'd be a little tricky. I don't have it memorized. Okay, so we're almost done here. So we're going to multiply both sides, or the whole thing, by 1/2. So that will give us our final answer, because then this will just be the secant cubed. So that's going to be 1/2 secant x tangent x plus 1/2 the natural log of secant x plus tangent x. And then that we would just put plus c. That's why I used a c1 there, because I'm multiplying it by 1/2, so that would give me a new constant. And that's the one I'll just call c. Alright, so that stepped it up a level there. A little bit tricky. We had to rearrange this, break it down, and then we got that same thing over here. I think we're going to have to do something like that down here also. Okay. So on page 491, example 4, they talk about, there's an example like this also. Do not interchange your substitutions when you repeat. So we're going to have to use integration by parts at least twice here. So when we go to do the second time, what they're saying is don't mix up your substitution, don't switch your substitutions. So that might not make that much sense now, but let's see how it comes out in the problem. Okay, so same thing I've been doing the whole time here. I've got this, basically the u side over here, u and du, and then I've got the v side over here, which starts with dv and then goes the other way, like this. Alright, so using Lie8, there are no logs. No logs, no inverse trig functions. Algebra doesn't seem. So the last two are trig and exponential. So trig comes before exponential. So since trig comes before exponential, I'm going to let u be the cosine of 2x, which leaves us with e to the 7x as our dv. So how did I choose that? I chose it based on that mnemonic device. Now, if we take the derivative of cosine, that's going to be negative. And it would start off as negative sine of 2x, but then we have to use a chain rule. We have to multiply that by 2. So I'm going to put 2 sine 2x dx. I didn't forget the dx this time. Okay. Now over here we're integrating. Now we integrated something like this on the front. So maybe you remember it was e to the 2x. So if we integrate here, e to the 7x. Now as we start to move over here, I could use a u substitution on the side here. I don't want to do that though. I don't want to take up that much time. So what I want to think about is if I take the derivative of this, what would I get? If I take the derivative of this, I'd get e to the 7x times the derivative of that times 7. And there's no 7 there, so that must mean that I have 1/7, because when I take the derivative of that, this 7 will come down and cancel that. So hopefully that's not that big of a deal. Alright, so remember we go ultraviolet, so that's going to be this times this. I'm going to put that in front of here. So that's going to be 1/7 e to the 7x cosine 2x. Alright, and then we're going to go this way. So that's going to be, so in the formula it's uv minus the integral ultraviolet voodoo minus the integral, and then we do these. So if we multiply these together, that would be minus. So we're going to have a minus and a minus. So that's going to be plus. Maybe I'll do that like this. Except now I can't factor out my fraction either, which I was going to factor out that 2/7. So maybe I'll move this over. So it's going to be minus because of the formula, and then minus 2/7 because of that. So that'll be plus, but I wanted it to be clear where that was coming from. And then we're going to have e to the 7x sine of 2x dx. Okay? So now this is very similar to what we started with. So that means that probably this isn't going to work very well for us either. So we can come over here to the side and we can set this up again. And so got that. Now I've got these labels over here, so maybe we don't need to write those down again. So probably this is going to be the trig one again. And that's what they're saying, don't switch them up. So the derivative of sine of 2x is cosine of 2x times 2 dx. Alright? And then this is going to be basically the same thing we have up there. So that's going to be e to the 7x. So this is going to be 1/7 e to the 7x. Okay? So that is all for this. Okay, so now we write that out again. Okay, so this is going to be 1/7 e to the 7x cosine 2x. Now, this is going to be plus 2/7. Now, this is going to split up with our ultraviolet voodoo. So that's going to be 1/7 e to the 7x sine 2x. Okay, minus this way, integral. So that's going to be 2/7 integral e to the 7x cosine 2x dx. Okay. All right. Now, that is what we started with. So now this is where it gets similar to the previous problem. So now we're going to take this and we're going to add that. Well, we also have to distribute this. I don't know if I want to do two steps at one time on this kind of complicated problem here. I don't know, we're in Calculus BC, we probably should be able to handle a couple steps here, right? So if I distribute this, I'm going to have negative 4 over 49 of this. And I want to add that to the other side. So I'm going to add 4 over 49 to both sides. So this one would be 49 over 49 because it's one of them. So that's going to be 53 over 49. So that's going to be 53 over 49 times the integral of e to the 7x cosine 2x dx. All right. And then we're going to have this again, so that's 1/7 e to the 7x cosine 2x, and then here 2 over 49 plus 2 over 49 e to the 7x sine 2x. All right, so did I integrate something? Where did I integrate first? So where's my plus c coming in at? Plus c. I'm trying to decide if I should have put my plus c in earlier or not. I'll think about that and come back to it. Okay, so let's finish this up. So we would multiply both sides by the reciprocal of this. So that's going to be, we're going to multiply by 49 over 53. So that'll just give us our original integral there. And then here, if I distribute the 49 into this, I have 49 over 7, which is 7. And I'll leave the 1 over 53 there. And then if I distribute the 49 here, the 49's cancel and I just have 2. So that leads to that. Alright, so normally, most of the time, when we break these down with integration by parts, we're actually going to take the integral of something, and that's where your plus c is going to pop in at that point. Now in this one, we never got something that we could actually easily take the integral of. We got down to this point, and we still had this integral here, but then we added that to both sides. So at this point, at some point in here, we're going to need to add that, because it's an indefinite integral, we're going to have to add that plus c. So definitely we need to have it in here. I'm not positive if we could have brought it in earlier, but we definitely want to bring it here at the end. So happy Halloween this week, and I wore this shirt in honor of that. So maybe send me an email about what this shirt is, and maybe I'll give you 1 point extra credit on a homework assignment for the first person who messages me about that. All right. Have a good day. It's about that time.